Welcome back. As I mentioned in the previous video that through this problem, we could actually see how the vapor pressure of a solution is less than the vapor pressure of a pure solvent. And the pure reason for the reduction in the vapor pressure of the solution is because of the fact that we are adding a solute into the pure solvent. Okay, I am going to show this problem mathematically to you to the idea of vapor pressure being reduced in a solution compared to a pure solvent, and why the misconception is not true, because you cannot make water boil faster by adding any kind of solute like sugar, salt, honey, whatever be it. You cannot just make it go any faster, right? All right, with that said, let's go ahead and rewrite Raoult's law first. Okay. And what does Raoult's law says? It states that the vapor pressure of a solution equals the mole fraction of the solute times the vapor pressure or pressure of the pure solvent. Okay. So the question clearly states it wants you to calculate the vapor pressure of the solution. So the question wants you to find this information for you. So this is a very straight plug-in check problem. As I said at the beginning of this concept, is you might just be able to do this problem without any discomfort, but if you don't understand what is really happening, the problem will be of no use, right? So we already know this vapor pressure of the pure solvent. You notice this information is already given to you, right? But it's very important to remember there are three major types of units under which pressure is measured. One of them is millimeters of mercury. The second is torr, and C. At least there's one more, which is Pascal, which we will get into if we come across one. And then the third thing is ATM. These are the three major units for pressure. Okay. Now, you don't need to do much in terms of this question, but if I specifically ask you to find the answer in ATM, then we will also look into that as a component of this problem. But in this case, you do not have to convert this millimeter of mercury to ATM, but it is advisable, which we will see in the second problem, which is an extension of this, that the international units, SI units, require all pressure is reported in ATM, right? With that said, we're going to have to first find the mole fraction of the solute, which means mole fraction of solute is moles of solute over moles of solute plus moles of solvent. Well, first we got to find the moles of solute, okay, which is 115 grams is our mass of the solute, which is glucose, and it's 1. And then the molar mass is given to you, which is 180 grams over 1 mole. Okay. Similarly, moles of solvent would be 485 grams is water, and then over 1 over water's molar mass is 18 grams over 1 mole. Okay. Now, if you do the math for this, (115) divided by 180 is 0.638 or 0.639 moles. And moles of solvent would be 485 divided by 18, which is 26.9 moles, right? Now we have to find the mole fraction of the solute, which would be 0.639 moles over 0.639 plus 26.9 moles, which would be 0.639. So let's do the math. plus 26.9, which is 0.023 moles. That's the mole the mole fraction doesn't have a unit. So let me actually, mole fraction doesn't have units. So that's 0.023. That's it. And now to find the vapor pressure of the solution, all you have to do is put the two informations together. So this times your vapor pressure of the pure solvent, which is 23.8 mmHg. That's millimeters of mercury. That's what it means. Times 23.8. That would be 0.552. 0.552 millimeters of mercury. Now this is the vapor pressure of the solution. Okay. Now you don't need to do much here, but what if I ask you what if I want this to be converted to ATM before it can be used? Well, you do not have to remember this conversion factor. 760 millimeters of mercury is 1 ATM. Okay, so 23.8 millimeters of mercury would be essentially 23.8 mmHg over 760 mmHg. Okay, this will give you our answer in ATM. Okay, so 23.8 divided by 760, which is 0.031 ATM. And now this can be used into the calculating the vapor pressure of the solution, which would be, the mole fraction stays the same. It's 0.023 times your ATM. The pressure is now expressed in ATM, and that will be times 0.023 would be 0. These two answers are only differ because of the unit of the pressure that we used, but both are correct. Okay. It all depends really on what you're aiming to get out of this. Okay. Now both forms are correct. Okay. I am going to separate this by a red line so that you know that this is an alternate. If I ask you to convert the millimeters of mercury in pressure to ATM and then solve for the vapor pressure of the solution, then you use method 2. Otherwise, you just stick with method 1, which is this. All right. So this is a very simple thing. Now, if you notice, right, that the vapor pressure of the solution is significantly smaller, right? Significantly smaller, this value right here, compared to this value right here, right? So if you're going to add 115 grams of glucose to your water, well, you can sure count on the fact that it's not going to boil at 100 degrees, all right? It's going to definitely be boiling at a slightly higher temperature. So this is the vapor pressure of the pure solvent. This is equal to the pot containing just the distilled water, and this is the vapor pressure of the solution containing both the distilled water and the glucose. Now you see there is a tremendous decrease in the values right here. So that should be an indication on how much the vapor pressure is reduced, and the vapor pressure of the solution is much, much smaller than vapor pressure of the pure solvent. And that's why we say that anything, water containing any other form of mixture is going to boil at a higher temperature. All right, this is a very fundamental problem, and I'm going to show you 2 different variations of it, and then also rekindle some of the knowledge, see if you really understood some of the Chem 170 material. I'm going to have you try that. All right, so stay tuned.